Okay, yeah. So what's up, everyone? So we just started the live stream. Before we start our lecture on binary search trees, I just want to make a quick few announcements about the rest of our dev communities. Give a little shout out. Look it up over here. Tonight at 7:30 p.m. We know we have mobile dev, so our my colleagues Azar and Kunza are doing a mobile dev meeting tonight, 7:30 p.m. And let me just make sure that that is actually, go back here to mobile dev. Yeah, 7:30 p.m. in this building, case room 138. And also for web dev, Manny is having a Zoom backend meeting, so meeting on doing APIs, at 8:30 p.m. over Zoom, so it's online. And so that's all I wanted to say on that. We also have a binary search night this Friday night at 8 p.m. So I also noticed that there's a bit of a conflict between the Smash tournament and the competition. I don't know, hands in the room, how many are planning to attend the Smash tournament? No one? Okay, so there's not that many people in the room, but they're saying they're not planning on joining the Smash tournament, apparently. But it's at 7 p.m., ours is at 8 p.m., just coding competition. It's binary search night, some binary search. We would send the link for the invitation on competitive programming, my mistake. Interview training, we changed the name, sorry. For interview training, we would just send you guys a notification that we started the competition, 8 p.m. Okay, so now that we got that out of the way, let's talk about a wonderful, brand new topic. It's not a binary tree, it's a binary search tree. So you all remember what binary search is, right? Disregarding what I said earlier about the competition thing. It's completely different. Who remembers what binary search is?
I wasn't here last week.
Well, so no one knows in the room.
I know what a binary tree is.
Yeah, we do.
2 child.
Oh, whoa. The screen doesn't see that. The screen does not see that. That was binary tree, yes. But what was binary search? Just, oh my God, still didn't see it. Can I zoom out? Okay. Yeah, just trying to make I guess I'll just write it differently. Okay, yeah, it sees that now. Sorry guys, the screen wasn't showing up. Okay, what was I asking? What is binary search? Who remembers binary search? Has to do with arrays.
So when you get half and a half.
Yeah.
And half.
Binary search only works when?
When you know the length.
No. So half and half. So what's the rule? What's the rule? How does it work exactly? Okay, so we know binary search is to search an element in a list in sublinear time. So instead of going through all the elements of the list or the array, you go through log of n. All right? So for instance, I have a list. I'm going to use a different color this time. So for binary search, let's say it's 1, 3, 5, 8, 13, 21, 27. So I have a sorted list of numbers. Do we need to look through everything to find an element in the list? Do we have to do that?
Go through everything. And
Yeah.
find what?
Find an element. Find a value.
Yes.
You don't. Well, this is a sorted list. So here's what you do. Here's the rule. Let's say I'm looking for 21. We'll just say 21. Okay? And we have two variables, left and right. We know the middle is, what's the middle, right? The middle is the average of these two. So it's going to be, this is 0 index 0 and 0, 1, 2, 3, 4, 5, 6. So what's the average between 0 and 6? 3. So that's just half of, well, not necessarily half. It's the middle. And you'll see why, I mean. 0, 1, 2, 3, right? A of m. So this is the important part. So what we say is compare the value we're looking for, which is 21, with the value in the middle, which is 8. And if it's greater than, then we say left is going to be here. And see, now we ignore this list entirely. We cut off half. We reevaluate which one's m, which is the middle, right? Have we found it? Yeah, so m is on the 21. And so, see, we don't have to go through all of this. It was very fast. We didn't have to go, ooh, we just skipped it all. So, that is binary search. Now, there's a way, yeah.
It only works if it's sorted.
Yeah, it only works if it's sorted, yeah. Only if it's sorted will this algorithm work, because if it's not sorted, then your whole greater than, less than, and moving the pointers of left and right doesn't make sense. So, maybe I'll keep this list of numbers. And I am going to create a tree, a binary tree, based off of this list. So it's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. All right. So it's going to be one, 2, 3, 4, 5, 6. Oh, it works out. Okay. Okay. And so, how do you think I'm going to put the values here?
In order with 1 at the top.
1 at the top? Are you sure?
That was a guess.
Yeah, it was a guess. Well, what if we ordered this like this being the middle? All right. And this is left and this is right. 1, 3, 5, 8. 13 is here. 21, 27. So in a binary search tree, the middle value is the root, right? And then everything to the left of it is less than. Everything to the right is greater than, much like in this list. So this is how one would look like. Of course, depending on how you insert a value, like this is also valid, disregarding this. It's strange. That will make it unbalanced, but that's on the topic of balanced binary search trees, which that's next lecture. That's not this one. But for this one, I guess what we could do is we could go over a few exercises. So let's say we have a balanced binary search tree. Coincidentally, you know, we just happen to have one. We inserted it in the right order somehow. So let's see, how do we search for a value? So let's say I wanted to look for, I wanted to search for 13. How do we do that?
Start at the top. And then
Okay.
It's greater than, you go to the right.
Mm-hmm.
And then it's greater than or it's less than, you go to the left.
Okay. And how do you iterate this process?
How do I get what?
How do you iterate through this process? How do you go from one step to the next? Actually, what is this? What is this data structure?
A node.
Yeah. So is it, to be specific, this is a binary tree node, right? And a binary tree node has what attributes?
Left and right.
And the value. Okay. So we could just use the for loop, right? Well, a while loop, I mean. We could use a while loop. Pull it up just to have it. So this, to search for a value, say 13, do the code right here. Okay, so we're going to search, right? So what can we do, right? We can have a current. And let's say this is root. So this is root. So I use cur is pointing to root. And while making sure to, let's see. Okay, they can still see. Okay. So what does this mean?
While it's true.
Mm.
And while there's a value.
Yes, yeah. So while there's an object, right? Yeah. So it's checked if it's still a valid object. So, and we said val that we're looking for is 13. We could be anything. And so what do we check? What could be the first thing we check? Yeah, okay. So while the value, so if, well, get rid of this smudge. So if, right, the value, this one, is equal to the current one, right, that value, what? We would return, well, we could do one thing. We could say, this. Well, let's say it's part of a function. We will return cur. What is cur?
The node.
Yeah, the node we're currently in. Exactly. Let's say it's not equal to. So what do we check? Right. And what's the check for left? What do we have to check specifically? What are values all the way to the left subtree? What are they in comparison to the root? Less than. So if the value is less than the current one, right, I would say that the cur, right, is going to be equal to cur dot left. All right. So we're going to say most likely unique values. There are unique values in the binary search tree. Okay, so if it's not equal or less than, what's the other option? Yeah, so else, right? And I don't need to, that's the default. It's just going to go to that. What do? I move to the right.
Cur is equal to cur dot right.
Exactly. Dot right. Okay? And so what's going to be the process here? So we're looking for 13, and we're here at root. I'm going to say, what happens? Where does cur go?
Right.
Right. So cur goes right. So it goes here. And then what? Left. So we found it. It's this one. And we returned that node which has the value we were looking for. So that is how you find the value in a binary search tree. Are there any parallels to what we did with the array? Yeah. And what's the middle is the root. And not only that, so we were here at this subtree in 21. 21 is the middle of the right. I could say partition the original one. What is it? 21. It's its own thing. Okay? Technically, each element could be its own tree. This is a tree, although just with one node. It's an interesting development. So what is one thing that we didn't have to worry about here that we had to worry about in this array?
Setting the new bounds.
The what?
Setting the new bounds for left and right.
Yeah, exactly. You have to know that left have to be 0 and then the length. You don't have to know the length here. All you have to know is the root. All you have to know is that you need to, change the current node position, and just follow along the path till you find your value. Whereas here you had to get left, right, calculate middle, and then move left over here, and then recalculate middle. We don't have to recalculate middle, right? We just know by default that the root is the middle of that tree. That is just a special rule of the binary search tree. Okay? So there's this other one that I wanted to go over. This was searching. And now we could go over, what's this one? Is this one easy? I shouldn't know what the problem is. I'll go over this one. So how do we validate that this binary search tree is a valid binary search tree? Okay, let me reword that. How do we validate whether a binary tree is a valid binary search tree? Okay. Well, just look at it. Is this valid?
Yes.
Yeah. Actually, no, that won't change anything. Oh, this will change anything. What about now?
No.
Why isn't this valid anymore?
Because 6 is greater than 5.
Yeah, and 6 would have to go here. So 6 cannot be, the right children cannot be less than 6. So that would invalidate it. So we want to check that a binary tree is a valid binary search tree. And let me have the original back. This was a 3. This was a 5. Okay. I think I'm going to have to, might need more space in this, Lazaro. I might need more space. Yeah. Okay. I think, yeah. So I'm gonna have to make some space. Erase this. Hell, I might even need to move just about everything. Okay, yeah, bear with me, guys. I have to rewrite everything. Okay. Let me erase this. Okay, so we want to validate this. We want to make sure that we can say, okay, this is a good binary. This is actually what a binary search tree, looks like. So what do we do? What could we use to validate this? Yeah.
No, I'm kidding.
You don't have a question? Are you sure? Yeah? He doesn't have a question. This is Lazaro, guys. We mess around with each other. So, what do we need to do to make sure that this is the root? How do we from the root this is valid?
Check that the left branch is smaller than the root and that the right branch is larger than the root.
Sure. But this has a recursive element to it, no?
Wait,
Yeah.
we go to you. Can you insert a number
Oh,
to the left of 5? The left child of 5 with a value of 2. would that be valid? As to what you said?
Wouldn't work in that case, no.
Yeah. Okay.
I think, can they see it?
I need this weird.
Okay, yeah, they do see it. That's invalid. But let's say I put a 4. What about now? Is that valid?
Seems valid.
Okay. The left is smaller, right? But see, this is a tree itself, and everything here is greater than this one. So, recursively speaking, in order to see if this is valid, you have to see that the subtrees are valid, right? Check this is valid, check this is valid, and it'll validate this. And on top of that, you have to keep track of, say, okay, so what's the greatest one to the left?
5.
Exactly. I'll point it. It's 5. What's the smallest one to the right?
13.
13? 13. So you need to check that the smallest one all the way to the right, which is the leftmost of the right, is greater than the root. And check that the greatest one to the left, so all the way to the right and the left, is smaller than the root. So you have to check that this is a valid binary search tree, this is a valid binary search tree, and that this is between this value and this value. Those are the checks you need to do to validate the whole thing. All right? And all of this is done recursively. So you do what you're going to do here, you're going to have to do here, you're going to have to do here. Right? So those are all the checks you need to say that it is a valid binary search tree. So I'm going to write a function. So Python, again, if you all are comfortable with that. Yeah. And it's going to be blue code this time because I like blue. I'm blue. Da dee da da. We're boomers. I like that song. What happened? What happened? If I was green, I would. I don't think that's the song.
I don't think so either.
That's like, I was green. I used to hear that, but then I'm like, no, that's my brain.
Someone told me that too.
But that's
Like,
your
there's
brain.
No way.
That's your brain making that connection. It's not actual. It's not an actual part. Okay. So we're gonna have a recursive function inside of this one, taking in a node. So when we're at a node, say the root, we have to check that the node is valid. And only when the node is an actual object do we actually do work. Because if we call on a null object and we do null.left, that'll give us a problem in compile or runtime. Yeah. And so, want to check that it's a valid object, and also it'll stop the recursive calls, right? This is our base case. If it is null, stop the recursive call. So we're at a node, and we want to validate that node that it is the root of a valid binary search tree, well, true or false. By the way, all the subtrees need to be valid. If even one is false, like say that was a 2, the whole thing just fails. All right? It will fail here, then it will fail here, and then it will fail here. Like it goes up, right? Single point of failure for the binary search tree. So we want to check our left and our right nodes, because we want to validate those, right? So I mentioned balanced binary search tree. We're not going over that, so we're not going to check if they're balanced, which I'll go over later. We just want to check that everything to the left is greater than less than the root, and everything to the right is greater than the root. That's all we're checking and validating that. So if node left, right,
Is this my code?
no,
No, okay.
maybe.
Are you sure? I think this is my code.
Is
it
it?
your laptop?
It was on my laptop.
It's my code.
No,
Remember, I answered this question.
you did. We never went over this together. Nah, it doesn't matter. We're partners, so it doesn't matter.
He's stealing my work. I'm kidding.
No, guys, we are collaborators. You know, we help each other out. This may happen to be his code. Right. All right. Well, let me just pause for a minute here. All right. So, what do you think's happening here? It's a lot of writing, huh? Okay. Well, what's this part right here?
It's called function.
It's calling itself on the left subtree. So it's going to return not one value, it's going to return 3 values as a tuple. You guys remember tuples, right? So a tuple is a set of values. Instead of just one variable, it's 3 variables. So in Java, it would be hard to return a tuple without using a auxiliary data structure library that they would give you. In Python, you can just return a tuple, and then here you're decoupling it, right? So really this is returning one object, but I can break it up into 3 because it's made up of 3 variables. Okay, so what's this variable here? Any guess of what this variable represents?
And lowest value.
To the left.
Yeah.
And then this one?
To the right.
To the right. So this is the lowest. So this corresponds to here. So it's the lowest one down there and the greatest one over here. Okay? And this one?
Same thing on the right.
Yeah. So, well, actually, L max would be the greatest one here. So we're doing it in this paradigm. Okay. And then we set this left equal to C. Now, this is the idea of a tuple. This is a 2 tuple. So it's 2 variables conjoined. And it's being stored in left, right? So left is sort of like an array. It's not really an array. It's different. But I can call left.lmin, right, as a variable to this. Does that make sense? Somewhat confused? Do you understand?
Just think of it as a data structure that holds 2 elements.
Yeah. And in fact, you can hold any number of elements, and Python will just do that work for you. So here it's 2, and the recursive call, it was 3, right? It was returning 3. And here I'm storing these 2 into left. So what am I going to do in node right? Well, I want them to say it.
Descendant, Rmax.
Yeah, exactly. Yeah. Rmin, Rmax, yeah.
Want to guess the rest of the code?
Well, your
You don't
faculty,
believe me.
right? I know you know the rest of the code.
No.
I know you do.
It's
It's
that
all
you
right.
don't know that I wrote it. You're saying that I didn't write that.
Is that you? I wrote this a long time ago.
You did not.
Go check it.
David,
Check it.
let me guess. You got 3 if statements.
Go check it. Check
If
it.
left and right. If left and not right. If not right and not left. Let me guess.
Okay, no. If not left and
Yeah,
not
it's the
right.
same thing.
Did you actually write this? Go.
Yes,
I
remember.
submitted this 6 days ago. Oh, you did? Oh, actually, since it was 6 days ago, Yeah, it might be your code.
Remember
Well-
we did the string part first? Doing like pre-ordering, I remember, I guess. And then I tried to do this, and then in the middle of the class, I was like, yes, I was able to do it.
No, that's not your code. I showed it to you. I showed it to him, and then he wanted to improve upon it. I didn't actually take that from you.
Dude, you're lying.
I don't know, guys. What do you think? Do you guys care? They don't
This
really.
is my code.
Do you guys care?
I think his enthusiasm outranks
Dude,
yours.
this is-
Leave him alone more.
Dude,
Well-
this.
Well, just because someone's passionate, that doesn't mean that they're honest. Anybody can do, you know?
I will go to the video, and I will go to the part where it said, guys, clap for Lazaro. He
Guys,
got the
guys,
code
guys. This is Lazaro's code. Whatever. I don't care. I don't care.
Well, you don't believe me.
I don't know. See, but
You made
he
them
does he have
clap
to
for
make.
me. Remember? Last class, you made them clap for me?
Guys, clap for Lazaro. This is his code.
Oh my god.
Clap for him. See, let's see.
I just want you to believe me.
Okay, I believe you.
Like all that.
Yes, they can. Well, they can hear me.
Trust me, they love us fighting.
It's entertainment, guys.
The camera's kind of crooked.
Yeah, it is.
Yeah.
I think it's because of the stick.
It's the stick now, dude. Is it the stick?
Like this part up here is crooked. Weird.
Look like Sonic the Hedgehog. I have spiky hair. I'm an anime character, guys. Oh, yeah, so see, tuple again. Into right. Okay. So I ran out of space. I need more space. I really don't want to erase that. What should I do, Laz? What should I do? Where else should I write this? I ran out of space.
Go with, and they're on the right side.
Yeah.
Do this here. If not,
They don't see it.
I'll move
That's the
this,
thing.
move it.
So do you actually you want to
There.
continue it there? I don't know if I'm gonna have space to actually write it in just this.
No, trust me, you have space.
I have
I wouldn't know.
Of course, you know he's not gonna let this down. He's not gonna let this down.
You denied me, you lied.
What? Okay, fine. And then I said at the end that it's yours because you wanted the credit. So there, you got it. See, I don't care. I got that calm and cool energy, okay? And he's got that. He's freaking out.
Dude, I don't like you to lie. You were lying.
Am I lying?
You were lying.
Well, if I lied, then it was not intentional.
Let me see
I'm
what
sorry.
time.
It was 6 days ago.
No, now see it gives you a specific time. And 23 hours ago. 23 hours ago. It's my fault. You were doing the lecture.
Was it
It's
3?
almost exactly 4 days ago. 7 days ago.
Yeah.
Which means last week during the lecture. Who was the only one that could code during the lecture? This guy.
Wait, so that was you?
Yes, because you were teaching the lecture. and I
You-
was doing it.
Why did you use my account? I wanted to
Because
solve it.
remember we were doing the strings part.
Guys, he took my account and he did the work on my
No,
computer.
No. We were
He
doing
took
strings.
it. He took it.
We were doing it in pre-order.
We
Remember?
were, you took my account.
You gave it to me.
I know, but I wanted. You could have given me some time to do it. Thank you for This is a lot. Thank you. I appreciate this. Okay, so what's this part? What's going on here?
If there's no left or no right node.
Yeah. So basically, yeah, exactly. So you just return the value as the. This would be. What is this? The minimum, right? Which is just the value, and then the maximum is just the value. So let's say I'm. Well, they can't see it anymore, but you guys can see it. We're in this one, right? Right. So what's the minimum?
27.
Yeah. What's the maximum?
27.
Right? And is this a valid binary search tree?
Yes.
Of course, it's just by itself. So, just value, and true. That's it. But let's say the left was the one, like here, right? But no right. What happens? So we check if left not right. Okay. What do we do then? What do we return?
You return no the left, no dot left.
No dot left. Well, the left has a value. Well, since the left is a value, there's a binary search tree in the left, right? Right. That means we have to get the max of that. So how do we get the max?
If there's no right.
Yeah. So actually, let me see something really quick. Yeah.
So if left and not right.
Well, actually,
that
so
would be max.
well, actually, let's just look at this one. Which is the max?
Yeah.
5. All right. So I'm gonna skip. So this value would be no dot val. Right. And this would be what? Actually, this one was. So left is right. So left 0. What does that mean?
The loop.
Hmm? This is a tuple, which is kind of like an array. You can access this value. So for the minimum, right? The minimum value. So see, we need to calculate the minimum so that answer will transcend to its parent when we get out of this recursive call. What do you want to say?
Oh, no,
Okay, so it's all right. So see, for here, we want to get the minimum to the right, and I have to get this value. So I have to move it up so I can give it to this guy, right? So I can compare this to this. So that's what this is going to do, right? And then I'm supposed to return a Boolean. So what's the Boolean I need to check here, right? Here it was just true because it was just a leaf, but now it's not a leaf. And we already checked that the left is, it only has a left subtree. So what do we do? What's the check?
If there's no right child.
Well, we already know there's no left, but there's no right. We already know there's no right. So what's the check that we make? Okay. So actually, right. All right. So, what's going on there in this check?
I don't know what left is.
Okay, so remember left? We put it here.
Oh.
Okay, so we're checking the max. So we're checking that the maximum value in the left is actually less than the root. It has to be. So that's this check. This could be true or false. And if it's false, then it'll just invalidate all the way up. In fact, it's a thing. We could have just made a whole.
String.
No. Stop recursive call.
Oh, yeah.
Yeah, we could have just done it there if this failed. And so here,
What is
that-
a triangle?
that's an and.
There's
That's
no
it.
and in Python, my dude.
What did you write? What did you write? What did you write? This is what you wrote.
So you did rate it.
You wrote that. You did that.
Of course I did.
All right, so whenever there's a mistake, he doesn't take responsibility for it, but
Wait,
whenever
you
it's good,
wrote and works
you
in Python?
wrote. Yeah, apparently it works.
Oh my god, I did.
So is it a mistake, man? Because it worked.
No, I did not.
It's his code, guys. It's his
I didn't know you
code.
could do that.
It's his code. You did it.
I know, but I didn't know you could do that.
Did you
Even though I
did you
it.
subconsciously just do that?
Yeah, I didn't throw an error. Wow. Okay, cool.
Okay, they can still see that. They can still see that. And LBST, what is and? So it checks for this boolean and this, right? What's LBST?
If it is a valid.
If the left child is a binary search tree. So that's this part right here. We need to validate the left child, which we already did here, right? I mean, we're recursively calling and checking, so we're already doing it. Okay, so we did the, so now we knew that the left had a subtree but not the right. But what if it was the opposite, right? What if, no, the stream isn't seeing this. This is a lot of work to just move the camera for this. What if the 27 had a right was 30?
And you do if not left.
Yeah, if not left, so we never set this. And right. Right. So what do we do then?
Return node dot val, comma, right, bracket is 0.
You see, yeah. So the maximum, well, the minimum is going to be the root, right? Because it's just right. And then the next one is going to be right. And we want
Oh, it's gonna be the max.
we want R max, right? Because here we're trying to get the max, and it's going to be all the way to the right. And we want to send that value up to the parent, right? So we want to check, so here we want to get, say, well, actually, let me just continue with this. And what's the, what are we checking exactly?
If it's greater than node val.
Okay. Well, which one? Which value is greater than node val?
The minimum, right?
Right. And that is this one right here. So the minimum of the right needs to be greater than the node val we're at, which is the root. And then what else do we need to check?
R, BSC.
Because we need to check that the right subtree, it's not a triangle, is a valid binary search tree, which is. And it is a Boolean, right? So this is the third value in this recursive return. And we're returning, what's the third value? A Boolean, exactly. So we know that L and R BST are Booleans. Okay. So what's the next check we do, right?
If
Well,
left, then right.
yeah, exactly. So what if what if the node, they have two, they have both. They have a right and a left subtree. So if left and right. So what's the rule now at this point?
Left 0 and right 1.
Actually, never mind. We actually, my bad, you guys. We actually don't need this. We don't need this check. we don't need.
Start over.
We don't need to check. We don't need to check it because we already checked that. Not right, not left. That failed. Left and not right. That failed. Not left and right. That failed. So that means that right and left are already set. Does that make sense? So we don't need a Boolean check for this one. We'll just
Just like an else.
no. We just do a return, right? Because we're returning, so we would escape. But since none of these return, all we have to do is a new return. So what do we return here?
Left 0, right 1.
Let's see. Yeah, exactly. Okay. And why left 0, right 1?
That is not the minimum of the left and the maximum of the right.
Yeah. And then what's the Boolean we return?
If left 1 is less than right 0,
Okay. But you're missing.
then and left BST and right BST.
You're missing a part. What about the node val? We need to check that it's in between the ranges, no?
Yeah.
And Python is interesting. You don't need an and. You can just
You can do that.
do that.
So cool.
It's really cool, guys. it saves you a lot of time in writing once you know all these like, Python, Java. It's like, oh my God, so much writing. Still, I love Java anyway. Yeah.
Not much.
No. Are you sure?
Yeah.
Okay.
So
Okay. Yeah. Yeah. Ask.
left one is the largest value.
Into the
on
left.
right side,
Yeah.
and
I don't.
right zero
The
is
smaller.
smallest value. On the right side.
I want to see that the node value is in between.
Yeah.
It has to be. It has to be in between. And then we also have to check what after this. We have to check the results of the left and the right. So L, BST, and R, BST, right? We need to make sure that we recursively said, hey, the left is a valid binary search tree, and the right is also a valid binary search tree, because if any of these fail, the whole thing fails, and we have to return that. When we AND false, what happens?
It invalidates the whole thing.
To false. It all goes to false when you AND just one false. So that's the idea. So they should all be true to return true. And so this is it. Then so let's get out of this recursive function. Let's call it, right? Let's say this is here. I ran out of space, and we're underneath. So L, R,
Call it outside.
I call it outside, right? Indentation matters, guys. Indentation matters a lot in Python. And what do we return? We're trying to return a Boolean. So what do we return here? The answer, right? Because it'll be the third one, because that's the Boolean. So we return if on root we had a valid binary search tree, which may be true or false. In this case, it will be what?
True.
Yeah, so in this case it's true, unless we did something wrong, or the binary tree doesn't have inserting the values in the right order. But yeah, so that in this case it will be true. Yeah, so this is the code. Who has the questions about this?
Did I have an else?
You did not.
I didn't.
You didn't use else. You don't need else because if the if statement doesn't actually go through, right, it'll just skip over, and it won't return. So it'll just go right on through. All right. Any questions about everything we've done? No? We get this. So we get that we need to, return left 0, right? Do you know why we do that? So the minimum to the left? Right. Okay. Because that is for up. Because this could be the right subtree. So let's say that when we're calling node, it is the root of a right subtree. And this part is going to be the right min. That's what this is. Make sense? The same thing for here, right 1. This could be all the way to the right, but we're in a left subtree. So we need to return that as the max for the left subtree in the parent. Okay? And these are just the Boolean checks, right? We need to compare the node value with, basically left 1 or right 0. Okay, and then also return whether the right is a valid binary search tree and the left is also a valid binary search tree. And it could be that there is no right subtree or left subtree. And there's this part right here. Okay, so this is validating whether the binary tree is a valid binary search tree. We didn't check if it was balanced. And I'm not going to go over that. I'm not going over that today. That's hard. That one's hard.
What does it mean to be balanced?
Okay, I'll briefly go into what it means. Really brief. I'm gonna. Okay, so. That. Is this balanced?
It needs 2 3s. Is that a reason?
No, that's supposed to be 13. 13.
Oh.
Now it looks like a B. It's like a B. B movie. Okay, is this a balanced one?
Yes.
Yeah, why?
Because it's got the equal amount of terms on each side.
So the depth is equal?
Yeah.
Okay.
On left, right?
Well, now. Is it balanced?
No.
No.
And why?
There's more right nodes than left nodes.
More left nodes than right nodes.
Is that really why?
Because the left side has 4 layers and the right side has 3.
3 layers? This is still a balanced one.
What?
It's still balanced.
It's still balanced. So here's the deal. It's only balanced if the difference between the left and the right, the depth, is 1. At most 1. It is at most 1. What's the difference between depth in the left and the right subtree? Yeah. There is no negative numbers, but let's just say there is. Is it still balanced?
Yes.
Yeah, it's still balanced. Let me put a 2. Still balanced?
Yes.
It's still balanced. Doesn't matter. Balanced?
Yes.
Still balanced. All right. Hot potato. Maybe I shouldn't have put it there. Okay, I'll just do an extra one.
No.
Why is it not balanced anymore?
Another layer of depth. 2 layers of depth.
Exactly. Yeah. There's a difference of 2. So it's 1, 2. Now it's no longer. Because at that point, this isn't really the middle anymore. That's the idea.
No.
Because then you could rebalance it.
Yeah, you can rebalance it, and what could be the new one? 3, exactly 3. Yes.
Isn't that cool?
So, and actually, how would we rebalance it?
You catch the 3 and then it'll
The 3 would be the new root, and what would happen with this 8? So, right. What will happen?
8 will be the right child and 5 the left of 8.
Okay. So it would be. All right. Yeah, and then the left
No.
is 5. Do you guys? Okay. Yeah, the stream sees it.
Yeah.
Okay. Yeah. So this is a new root, and the right child will be 8, which was the old one, and then 8's left child would be right's previous right child, and that's it. You're just changing the pointers around. Okay. I'm not gonna get too in depth, but that's the basics of having a balanced binary search tree, and has to do with depth. Because in the extreme case, I'm gonna erase this. That's fine.
Wait, is that balanced?
Okay. Another thing about it, it's a recursive step, so you have to recursively do it. So once you get this, you recursively balance subchildren.
Oh, interesting. Cool.
Yeah. So say in the extreme case, in the way you insert values, you get something like this. This is a binary search tree, technically. Now, is this balanced? No. What does this look like to you? A regular linked list. A linked list just goes, and searching would take, instead of log time, what's it going to take now? Yeah, this is going to be a linear search. So it's no longer log n binary search. It's just a linear search. So that's why we need to have a balanced binary search tree, because then you might end up with this, and it defeats the purpose of having a binary search tree in the first place. That's why we need to check for that. When we will do that next lecture, I'm thinking about putting a stop right now. Yeah. Well, you had a question? No, okay, all right. Thank you guys. Thank you for coming. Be sure to, if you can, attend the binary search night, the mobile dev. Also, this Friday, I didn't mention this before, we're also having a type racer event. So it's like a mini competition. It's not as fun as Smash, but you get to show off your typewriting skills, your speed of typewriting, right? Just talking about type racer. So, be sure to attend that. You might win a prize if you're in. Yeah, I mentioned that already. Yeah, 8 p.m. binary search night. Type racer is in person. It's at 5 p.m. Where's it?
And lead code questions will be sent out tomorrow.
Yeah, lead code questions will be sent out tomorrow on this topic. I think did I send this actual question?
I'm not sure about adding.
Okay. If I didn't put it there, we'll add it. We'll add if I didn't do it. But you'll get a ton of other questions about binary search trees. I think 12 of them. Well, 24, because it's 12 beginner, 12 advanced. All right.